Okay, so right now we're going to be looking at figuring out the pH of a salt solution, and specifically this really, really ugly solution. So before we do anything, I want to break down what these two things are and why we don't really have to worry about it that much. So if you take a look at this, this is a really long, this is aniline chloride. So this is aniline and this is chloride. This right here, all of this right here is a positive ion and chloride is a negative ion. Now we're going to throw this into water. And one of the things that we need to know, and I don't know if you remember, and if you haven't looked back, you need to probably watch determining whether a salt is acidic or basic. But this is a salt because it's an ionic compound. And again, it has two parts, a positive and a negative. And what we do is we look and we see whether either of these two things, if we were to throw it into water, would it actually do anything? And I would say almost 95% of the time when they give us something like this, what they're going to do is they're going to give us the thing they want us to work with, and then they're going to give us a spectator ion. Normally, it'll come in front of something. It'll be like an Na in front of something, and we're like, you're a spectator ion. But they do the same thing with like halogens. And the way to think of this is that if we were to take this and throw it into water, could it grab hydrogens? And since Cl minus is the conjugate of HCl, which is a strong acid, this Cl minus is going to do nothing. So as far as we're concerned, this guy doesn't exist. In fact, I'm going to put this in with like this, which means that what we have left to work with is this aniline acid. Now, this right here, this is aniline, C6H5NH2. If you notice over here, this is C6H5NH3. You see there's a 3 here versus a 2. What is the difference between these two? Well, this right here has one more hydrogen than this does. So this is our base, and this is the conjugate acid. And so what essentially we're doing is we're throwing this acid into water, and we're going to work with it. So let's go back to our original problem. And essentially what they're doing is they're giving us a concentration of an acid. Remember, we don't have to care about the Cl minus anymore. And if they give us the concentration and they give us the Ka, then we can solve for the pH. This is like every other weak acid problem. But the one thing we have to worry about here is they didn't give us Ka. What did they give us? They gave us pKb. So the first thing we have to do is we have to find a way to get from this to Ka. And so the quickest way to do that is to remember a couple of things here. Isn't Kw equal to Ka times Kb? So if we know what our Kb is, we know that Kw is always 1.0 times 10 to the negative 14, right? So we can solve for Ka if they give us the Kb. Now, do they give us the Kb right here? Not exactly, but they give us the pKb. And since we've done this a few times before, and maybe if you haven't, this is the first time you're watching a video like this, P is equal to the negative log of something, right? So if I said pKb, that would be equal to the negative log of the Kb. But if I want to get Kb by itself, we're going to go 10 to the negative pKb. Now, if you're wondering, like, how in the world does this work? This is logarithms in action. And so just to have this set up for us to begin with, we're going to do these two steps with this pKb first. And so we're going to go, and I'm going to, because I don't want to have to rewrite this, just going to lasso this buddy right here. And we're going to go Kb, oops. I'm going to put this down here and say is equal to 10 to the negative, let's put that up a little bit higher, pKb. So how do we solve this then? Well, we want to figure out what our Kb is. We're going to go 10 to the negative, and then they give us 4.87. And when we do 10 to the negative 4.87, we end up with, via doing math off screen, we end up with the Kb equal to 1.349 times 10 to the negative 5. Now, this only has two significant figures, but I'm going to keep a few extras here because we're not at the beginning of a problem. Now, this is 1.34 times 10. This is our Kb, but since we're dealing with an acid, this anilinium is an acid, we need to do the Kw equals Ka times Kb portion of this. And when we rearrange that, we're going to end up with Kw all divided by KB is equal to KA, and that's really what we're looking for. So all of this right now is to get back to our KA value. And when we do that, it's going to be 1.0 times 10 to the negative 14 divided by this number that we just got, 1.349 times 10 to the negative 5 is going to be equal to my KA. And so my KA for this problem is going to be equal to 7.487 times 10 to the negative 10. Again, this was done off screen, but this is the one number that we really need. Everything else we really don't care about. So what I'm going to do is I'm just going to lasso all this stuff right here. I'm going to get rid of it. If you want to, you can pause the video if you need to redo this here. But this is now our KA that we're going to use for the rest of our problem. So we're going to put this up here, and this is what we're going to use. Now, once we've done that, now we're really close to doing an ice problem. So what we're going to do is we're going to take anilinium, so this part right here, and we're going to throw it into water. Now, I do not want to write this over and over and over again. In reality, what this really is C6H5NH3 plus. Remember, this is a plus. But I'm going to make this into An plus. It works the same way. Again, and College Board will be okay with you making it simpler. So we're just going to do what we always do, is we're going to take what we're trying to work with and we're going to throw it into water. So I'm going to write N plus. We're going to make that aqueous because it is dissolved in water, plus H2O. And we know that it is at equilibrium, and that's going to form. So since this is an acid, what is it going to do? It's going to donate a hydrogen to this. And that probably would have been better to write it as ANH plus. That would probably make it a little more indicative of what's actually happening over here. So I'm going to make it ANH plus over here. And then on this side, I'm going to make it AN by itself, right? And then this H plus right here is going to join the H3O plus. So what I'm going to end up on this side having is plus H3O plus. And if what I just did here, by not writing NaH plus, confused you, then you could just write this out as is with a plus on the end of it. And then on this side, all you'd end up with is this right here is what this is right here. Yeah? But because I did it this way, we're going to keep on going this way, and we're now doing ice problem. Now, they're starting us off with 0.74 of this, and we have none of this and none of this, which indicates that the reaction is going in this direction, which means that we're going to lose stuff from this side, and we're going to gain stuff on this side. And because it's a 1-to-1-to-1 ratio, those are supposed to be circles, but 1-to-1-to-1 ratio, if I were to lose X here, I'm going to gain X here and gain X here. And then at equilibrium, I'm going to have 0.74 minus X, X, and X. And this is going to look awfully familiar because once we do that, if we write our Ka for this expression, it's going to be the products raised to their coefficients all over the reactants raised to their coefficients. And note again that I was deliberately not putting this in here because that is a liquid. I got a little careless in not writing that. Liquids never go in. So all we're going to do is we're going to plug these values into here. And as we like to say in my class, we are going to dead frog it, 0.74 minus X. And that is going to be equal to 7.487 times 10 to the negative 10. This is an incredibly small K value, which means that the things that are on the top, aka the X's, are going to be so small compared to what we started with. In other words, saying is this amount here is going to be so little compared to this 0.74 that we can get rid of it. We call this the 5% rule or the weak acid. I can't remember what the term is they use, but they essentially say that it's approximation, I guess they call it. But we can get rid of this. We'll call it the 5% rule, saying that this X is less than 0.74, and that makes this a lot easier problem to solve. We're just going to go X squared. Instead of having a polynomial, we're going to go X squared is equal to 7.487 0.87 times 10 to the negative 10, all of that times 0.74. Now, again, the way they solve in ALEKS and in general is they keep these extra significant figures to the very end, and at the end they go back and they take care of it. Now, in this case right here, we're going to have to do the square root of both sides, and when we do that, we're going to end up with our x being equal to 2.354 times 10 to the negative 5. Now, we just solve for x, but we need to acknowledge what x is actually equal to. Both these x's, x is equal to the base, but also x is equal to the H3O plus. And that's what we really care about because they want us to solve for the pH. So we need to somewhere in this, not just write x is equal to this, but we need to say that it's equal to our H3O plus as well. Now, if we wanted to, we could also say it's equal to the N, but we don't care about the N because they're not asking us for it. What they are asking us to do is solve for pH, which is going to be the negative log of our H plus concentration, which is this guy right here. And so we're going to plug that in, negative log of 2.354 times 10 to the negative 5. And when we do that, we're going to end up with a pH of 4.6282. Now, this is important because in this problem, they asked you to round this to one decimal place. But if it was an actual AP exam, we take a look at the significant figures they gave us. We have 2 right here, and we have 2 right here. Remember that whenever we have a P of something, the significant figures count at the end. So in reality, if we're doing this, we'd have to count, remember, we ignore this, and we'd have to count 2 spaces over, and we'd write 4.62, and then this 8 would round this to 3, so it'd be 4.63 would be how we do it on the AP exam. But because they asked us to do it in ALEKS to just 1 sig fig, we're going to write pH is equal to 4.6. Now, one last thing here. If you take a look at this x value right here, often what they'll do in a problem is they'll ask you to solve for the percent dissociation. And what that means is this. Do you see how x is what left this original amount? So if you were to take this x value and you were divided by the original amount, which in this case is the 0.74, and then you multiplied that by 100, you'd end up with the percent dissociation. Now, part of what we have said in this problem is that we used the 5% rule. So we're saying that this x, when we divide it by this, it's going to be less than 5%. And we can assure ourselves of that because if we take a look at the actual number, and it's 2.354 times 10 to the negative 5, if I were to divide that by 0.74, we would end up with a number that's much less than 5%. So it works all the way around. This is our final answer, and I put stars around it. I hope this has been helpful.